Maybe
Right.
just like flip back and forth between your slides and make sure the pointer works as well.
Oh, where's the pointer button? This one?
Yeah, that.
Oh, well, there's a laser pointer. Oh, well, I guess I'll, oh, whoops. So, oh, yeah, it works now.
Seems to work? Okay.
Yeah. Sure. Okay. Should I start?
Yeah, I'll just announce the session.
Oh, sure.
Quickly. Okay, welcome everybody to the first session of the day on deep learning. We're excited to have a bunch of wonderful speakers for us today. So before we get started, I'll just share the logistics for those of you who are new to the conference this year. All talks will be 10 minutes in length, including time for questions. So for speakers, what I will do is I will time your talks, and I will flash up this note when you have 2 minutes remaining. Okay, so without further ado, let's get started. Our first speaker is Itai Safran, who will be telling us about some exciting work on depth separations in neural networks.
Thank you. So this is joint work with Daniel Reichman and Paul Valiant. So in a nutshell, this talk is about showing a separation between depth 2 neural networks and depth 3 neural networks. And the main question that we consider, can we show an exponential separation? And the answer is that yes, we can show such a separation even for a function which is easily computable by a depth 3 neural network. So a few preliminaries to get out of the way before we can begin. The architecture we consider here is a fully connected feed-forward neural network, as the standard definition you may know. And we consider activation functions with very mild assumptions. So this includes in particular common choices such as the ReLU, a sigmoid, or a threshold. And essentially any reasonable activation function you can come up with is one that our result is valid for. So when I say that we approximate a function using our neural networks, what do I mean? So formally, we consider a standard L2 approximation notion where we have some underlying distribution on the data, and we sample some instance from that distribution. And then we look at the expected square loss of when we try to approximate a target function f using our neural network n when we draw from this distribution. So the reason why this notion of approximation is interesting is because it implies lower bounds. Such lower bounds imply the difficulty of learning when we show such lower bounds for a family of certain functions. For example, if the neural networks we consider are a certain depth 2 neural network architectures and we show a constant lower bound, say this quantity over here has to be at least 1, then this means that this class of functions cannot learn this problem, this learning problem, when the underlying distribution of the data is this particular distribution that for which we have this lower bound. So this is why such results are meaningful, because if we can't approximate, then clearly we cannot learn. So by now it is already well established that depth may be necessary to get a compact representation of certain target functions. That is, there are functions that require at least depth 3 to get a good approximation of. This was first shown by the seminal work of Ohad Shamir and Len Eldan in the Colt of 2016, and there were many such works that followed. And the results basically have the following flavor. So we can approximate efficiently if we use a depth 3 neural network. So a depth 3 neural network NDeep will be able to get to epsilon accuracy, where the size, the number of neurons in the network, scales polynomially with the relevant problem parameters. However, if we attempt to approximate the same function and with respect to the same distribution on the data, we won't be able to get the same accuracy of epsilon unless the width of the depth 2 network is exponentially larger than that of the depth 3. So this establishes that depth 3 can be exponentially more valuable than depth 2 neural networks in certain cases. However, despite these growing number of results, There is a problem if we examine these problems a little bit more closely. So if the accuracy parameter epsilon scales with d to the minus 2, for example, which actually happens in some of the results we have in the literature, then the lower bound becomes too permissive very quickly. This is because when we look at machine learning problems, then d, the input dimension, is roughly in the magnitudes of tens of thousands in some cases. So having such a lower bound is not particularly strongest lower bound that we can hope for. Even more so. So if we show a matching upper bound, then this might be considered by many as a very strong positive result, right? If I can approximate a function to accuracy 10 to the 8, 1 over 10 to the 8, that's a very good approximation result. So these bounds are essentially too permissive. But there is a way to circumvent this. If we look at the accuracy parameter epsilon over here, we can whack it by scaling the target function f. So if we have a lower bound for a function which we cannot approximate to accuracy epsilon, which may scale with d to the minus 2, then if we multiply f by d and we get a new function, d times f, then we cannot approximate this function to accuracy better than d squared times epsilon, which is now a constant. This is because the family of the neural networks that we consider here is closed under such linear scalings because we can simply scale the weights of the output neuron. So this bound, this lower bound is valid if and only if this lower bound is valid. So we can get a constant lower bound, a constant accuracy lower bound in such a setting if we have such accuracy for a different lower bound. But there's obviously a problem here. So once we whack the accuracy parameter here, we have another problem with a different parameter, which is the Lifshitz constant. Now our target function d times f of x has a Lifshitz parameter which scales with d. This is because if f was 1 Lifshitz, this new function is now d Lifshitz. So we still have that the input dimension manages to creep in inside our parameters. So, but luckily there's also a way to circumvent this, and we can also whack the Lifshitz parameter L. We can do this simply by scaling the input distribution. So if we have our previous lower bound over here, it is valid if and only if this lower bound here on the right is valid. By scaling the distribution by a factor of d, we simply draw an instance and multiply all coordinates by d, and this corresponds to scaling the input by a factor of 1 over d in the distribution. And this is valid because our family of functions, depth 2 neural networks, is closed under this such a scaling because we can scale the weights of the hidden layer now. So we can get a lower bound with constant accuracy and a constant Lifshitz parameter. This has a constant Lifshitz parameter again after we do all these scalings, and everything seems fine. However, we did scale the input dimension, and now we have that the input dimension scales with d. The underlying distribution scales with d. So it doesn't matter what we do if we consider all existing results. Whenever we whack one parameter, the input dimension manages to creep in somewhere else, and there's really no way to get around this. So this begs a very important question. So when we say that we have exponential dependence in the input dimension d, does it truly stem from the input dimension? Maybe there's some very clever construction which is always polynomial in the input dimension d. However, it may be exponential in one of the other parameters, and since these parameters were forced to scale with d, we get this exponential dependence in the input dimension. So it's not clear who's to blame for this exponential dependence. It could be a different parameter than the actual input dimension. So we observed this trade-off in a cold paper from 2019, together with Ronen and Ohad. And we asked the following question. Can we show a depth separation where the input dimension does not creep in, where the difficulty in approximation truly stems for d? And to ask this question, we ask whether we can hold all the other parameters fixed so that they do not scale with d, and can we show under such a setting an exponential separation between depth 2 and depth 3? So we asked this question in 2019, and we also showed that this would require new proof techniques, and today I can tell you that the answer is positive. We can show such a separation result. So our result, more specifically, is the following, and in the same flavor of the previous results. There exists a depth 3 approximation, which is efficient, requires polynomial width and all the relevant problem parameters, where the distribution is supported on a domain of bounded radius with respect to a target function which has a constant Lifshitz parameter, and where the accuracy lower bound for depth 2 is also an absolute constant. So we cannot approximate using depth 2 unless the width is exponential. So to briefly tell you about the high-level proof idea, the key idea is to embed a continuous version of a Boolean hard-to-approximate function in the unit ball. And the reason this makes sense is because we have strong lower bounds for certain Boolean functions from theoretical computer science. And basically, threshold circuits are neural networks with a threshold activation, which is very similar to neural networks. And the hard-to-approximate function that we consider is a continuous version of the IP mod 2 function, the inner product mod 2 function, which has very strong lower bounds. In the literature, specifically, we use a reduction to this classical result in the literature by Hajanal et al. And the upper bound follows rather easily by doing a two-step approximation using depth 3. We use the first hidden layer to approximate the inner product, and the second hidden layer to approximate the mod 2 function. So I'll briefly tell you about the main challenges we had in showing the proof of this main result. So when we scale the hypercube to fit inside the unit ball, we need to factor it by 1 over root d, which scales the Lifshitz parameter. And of course, this is not desired in our setting, so to circumvent this, we also map it to a product with a set which is well spread over the unit ball. And we use a Rademacher complexity argument to show that the hardness in approximation persists. And this also allows for constant distance between all the points that we map to. The second problem is that if the square loss is at most this constant, then this means that the absolute value loss is roughly 1 over 20, which intuitively means that we compute 95% of our inputs correctly, of the IP mod 2 inputs correctly. But to use the reduction, we need to compute 100% of the inputs correctly. So we show a worst to average case reduction in this setting by mapping our data to a high-dimensional version while preserving its IP mod 2 value and making the input seem very uniformly random in that high-dimensional space, which allows us to use the known result from by Hajanal et al. So to summarize, we have shown that the curse of dimensionality does affect depth 2 approximation, even for functions that can be approximated using depth 3. And this time, the actual difficulty does stem from the input dimension itself. So this is why it is difficult to approximate in this particular setting that we have shown. And thank you very much.
Okay, thanks for the great talk. Any questions from the audience? Please raise your hand. Okay, I have a very quick one. Can you comment on the scope of, I mean, it's a very open-ended question, but is there a sense in which you think your techniques could be useful if you wanted to do greater depth separations, say 3 to 4 or 4 to 5 or etc.?
Oh, wow. So yeah, I wish. I don't think that anything here is valid. So we do use reduction techniques from threshold circuits. So if a separation result for threshold circuits that works for depth 3, a lower bound for depth 3 that is, would exist, then yeah, we can use those, but unfortunately we don't have such results.
Thank you. Okay, so we will move on to the next talk on complexity of injection, injectivity, and verification of ReLU neural networks. we'll get started with the next talk. The presenter is Moritz Grillo from TU Berlin.
Yeah, thank you. Hello, everyone, and thank you for coming. I will present the paper Complexity of Injectivity and Verification of ReLU Networks, and this is joint work with Vincent Fröse and Martin Scutella. So we can think of a neural network as some parameterized function, which, depending on the parameters, computes a function from the input space to some output space. And what we refer to as training of the neural network is to optimize these parameters in order to fit the function to some data set. And the kind of questions that we're addressing in our paper is, now given such a parameter, maybe after training, what can we then actually say about the properties of the function that this neural network computes? And of course, we can evaluate the function pointwise, but what about more structural or global properties, such as, for example, injectivity, which is important whenever invertibility of the function is required, for example, in inverse problems. And alongside injectivity, we also study surjectivity, which, despite being another fundamental mathematical property, it's closely related to network verification, which can be described as follows. So given some set P in the input space and some set Q in the output space, can we somehow verify that everything that is in P gets mapped to something in Q? And these kind of questions are particularly important whenever the network is used in safety-critical applications. And we study these questions for ReLU networks. So a ReLU layer with the input and M output neurons is given by some weight matrix W and a bias vector B, and computes a map by taking some input vector X, multiplying this with the weight matrix, adding the bias vector, and then applying the ReLU activation function, which just component-wise maps everything that is negative to 0. So here on the right, you can see an illustration of such a ReLU layer, and now an output neuron first computes an affine combination of the input neuron and then takes the maximum of 0 and this output, and this affine combination. And geometrically, such an output neuron induces a hyperplane consisting of the points where this affine combination is precisely 0, subdividing the input space into two half spaces, one where the neuron computes an affine combination and the other one where it simply computes the 0 map. And then we have, of course, such a hyperplane for every output neuron. So what we obtain in total is a hyperplane arrangement that subdivides the input space into polyhedral cells, such that the function computed by the layer is affine linear on each of these cells. And now we want to study injectivity for the function computed by such a ReLU layer. So formally, we were given the weight matrix and we were given the bias vector. How can we decide if the corresponding function is injective? And there's a characterization from Pudwala et al. Saying that the map is injective if and only if on every cell in this polyhedral subdivision, the affine linear map on this cell does have full rank D, where D is the input dimension. And since it's known since the 70s that the number of cells that are induced by such a hyperplane arrangement is at most m to the d, this gives us an exponential time algorithm to check injectivity simply by iterating over all the cells, computing the linear map, and check if it does have full rank or not. But well, that's an exponential time algorithm. This does not scale well, so the question that arises here is if we can do better, if we can maybe even achieve polynomial time. And here the answer is most likely no, since we can show that the problem is co-NP complete. So unless P equals NP, there cannot be a polynomial time algorithm deciding injectivity for a ReLU layer. And I want to give a very quick glimpse at the proof. So the key step is that we construct certain ReLU layers from given digraphs via so-called graphical hyperplane arrangements. And then this allows us to interpret injectivity of these constructed ReLU layers purely in terms of the underlying digraph. So deciding injectivity becomes a certain cut problem in these digraphs. And then we show hardness for this cut problem, which then transfers to the hardness of the ReLU layers, of deciding injectivity for the ReLU layers. So there is no hope for polynomial time, but still there remains the question if we can do something better than simply checking every single cell. And here the answer is yes. So we can design an algorithm that decides injectivity for a ReLU layer and has a runtime roughly of d plus 1 to the d, where d is the input dimension, times something polynomial in the number of ReLU neurons. So here the superpolynomial part of the runtime only depends on the input dimension d, but in the number of hidden neurons, it's a polynomial of constant degree. So this means that the problem is still tractable in small dimensions, and in a parameterized complexity language, this means that the problem is fixed parameter tractable for the input dimension d. And that's all I wanted to say about injectivity. For the remaining couple of minutes, I want to talk a bit about the complexity of deciding surjectivity and verification of ReLU networks. And I will start with surjectivity and then move to verification. And the first thing that we can notice is that the question of surjectivity does not make sense for a single ReLU layer because we only have non-negative outputs, so the map can never be surjective. So we study this for a slightly different architecture where we have an additional output neuron that is simply a linear combination of the ReLU neurons. So now the question that we're having, given all these weights, the input and the output weights, is the map surjective? So does it attain the whole real line? And the first thing that we can observe is that, well, we can assume without loss of generality that we do not have a bias, since, roughly speaking, the bias does not help us in making the map more or less surjective. And if we do not have a bias, then we can show that the problem of deciding surjectivity actually boils down to just finding one point in the input space where the neural network attains a positive value. So attaining a positive value and surjectivity is really equivalent in this case. And how hard can this be to just find one point where the function is positive? But this problem is actually already hard. So we can show that deciding positivity is NP-complete for a one hidden layer neural network, which then also implies that to decide surjectivity is also NP-complete. And this hardness of positivity has some further implications for the verification of neural networks. So it implies that for any ball B in the input space, there cannot be an approximation. So we cannot design an algorithm that approximates the maximum that the function takes on, that the function computed by the neural network takes on this ball. Basically any kind of approximation that you can imagine in polynomial time, again, under the assumption that P is not equal NP. And another straightforward implication of the hardness from positivity is that it's also already co-NP complete to decide if a two hidden layer neural network computes the zero map. So to conclude, we've seen a lot of hardness results, and which means that we cannot expect to find a polynomial time algorithm that decides basically any basic properties of a ReLU neural network. So including injectivity, positivity, surjectivity, approximating the maximum, or even deciding if it is simply the zero map. And since these results, these hardness results already hold for very restricted architectures, we can also conclude that there's a lot of complexity already going on in very shallow neural networks. And we have some open questions. So basically the only positive result that we've got is that we can design an algorithm that decides injectivity for a ReLU layer, a parameterized algorithm where the parameter is the input dimension. But this also only holds for one layer, and we wonder if this tractability in small dimensions also extends to deep neural networks. And we have the same question also for positivity. There we have also the hardness, but we don't know if we can design an FPT algorithm for positivity. And I will also present another perspective on this problem in the open problem session, where we translate this problem into a more polytopic problem. And that's all I want to say. I thank you a lot for your attention, and I'm happy to take any questions.
Okay, thanks for the nice talk.
Hey, very nice talk, thank you. I have a basic question about what model are you using? The bit model, or what model of computation are you using when neural networks are dealing with real numbers? You can't possibly use that. So rational numbers, bit representation, does that come into play when proving these results or not? So the numbers that go into the neural networks, well, I just think about them as reals, but if you're talking about computational results, obviously you can't do that. So you must be thinking about how many bits there are in the architecture, so all these scaling questions, or it's completely irrelevant somehow to the construction?
It's completely irrelevant, so we can assume that the input, that you can feed real numbers into the network, because the characterization of injectivity and also later of surjectivity, that's purely combinatorial. Sorry? I mean, yeah, okay, no, the weights, I mean, what matters are the weights. So the weights, they should be rational. And the weights need to be polynomial, the weights are part of the input. So the weights are rational, and the encoding size is part of the input.
Okay, thanks for the nice question. We maybe have time for one more question, but we can also move on. Okay, yeah, let's thank the speaker again. So, is the next talk disk quant design?
I have a question. That's okay.
Yeah.
Yeah. So if we had assumptions about the network, for example, that it's trained using gradient descent from a random initialization, will the hardness results still hold?
I mean, it depends, of course, on the initialization, but I don't really know. We haven't looked into it. We had some experiments where we sampled random weights, but we don't have any rigorous results for assumptions on the weights.
Okay, thank you.
We'll move on to the next talk, which is called Disk Quant, a quantization method for neural networks inspired by discrepancy theory.
Okay, hi everyone. I'm Rini, and I'm going to be talking about a quantization method for neural networks inspired by discrepancy theory. And this was a joint project with Arthur's backers, Jerry Chi, Li Zhang, Jana Kulkarni, Thomas Rothfuss, and Sivakanth Gopi. So the problem that we're trying to solve in quantization framework is that, in general, storing and running inference with large pre-trained neural networks, in particular LLMs, is very computationally expensive. And one way that we can approach solving this problem is through quantization, which means that we're going to approximate and store the trained weights of the network by rounding them to some good low-bit complexity representation. So for example, we could think about the weights, the training weights and the data as being float 32, and rounding them in some clever way to integer 8 for faster computation and for more efficient storage on edge devices, for example. So in our paper, we focus only on post-training, weights-only quantization. There are lots of other frameworks, including quantization-aware training, where you actually incorporate the quantization into the training process. So post-training meaning that we're going to look at models that already have weights, and we're going to round them in our application in one shot. And weights-only meaning that we're not going to round the activation separately. And there are two steps to post-training quantization. The first is finding a good low-bit quantization grid. And the second is rounding the weights to the quantization grid in some clever way while minimizing the error that we incur. And there are two types of error that we're interested in. Our algorithm specifically focuses on step 2 for any given quantization grid. And I'll show in our experimental results that we actually validate that we can use multiple different quantization schemes and still get good results. So as I mentioned, there are two types of error that we want to consider when we're looking at the results of a particular quantization scheme. The first, the easier type, is the empirical error. So we're given some fixed samples from our data distribution, and we'd like to minimize the error on these samples. But more importantly, we're interested in the generalization error, which is the expected error for unseen samples from our distribution. And so the fundamental theoretical question that we would like to answer with our project is, how many samples do we need to get good provable generalization bounds? So there are a couple of challenges with this problem. One is that, of course, we don't actually know our data distribution, so we need to approximate it and make some assumptions about it. And a bigger challenge is that we're working with extremely large networks. So the experiments that we run are on these two networks, which have 3.8 billion and 8 billion parameters, respectively. And so in general, the number of samples is going to be much, much smaller than that, particularly since our goal is efficiency. And one of the theoretical questions we need to consider is what empirically motivated assumptions can we make that will guarantee generalization, at least in expectation. Most of the literature on post-training quantization so far is focused on finding good quantization grids. There hasn't, to our knowledge, been a lot of research on quantization rounding approaches that are agnostic to the quantization scheme. So the two approaches in the literature are round to nearest, which is just the greedy approach, which is often used as a baseline where you round each weight to its nearest point in the L2 norm in the quantization grid. And the state-of-the-art model previous to our paper is the GPTQ algorithm, which was an ICLR 2023 paper due to Fronter et al. It's a data-driven algorithm that's designed to match the outputs of the model layer by layer, which differs from our model because we round all of the weights at once. And the algorithm that I'll be presenting in this presentation is our disquant algorithm, which is based on discrepancy theory. And this is just a preview of our experimental results. Our results are shown in blue, and I'll come back and talk a little bit more about that at the end. So to define our algorithm, I need to briefly introduce discrepancy theory, which is a tool from combinatorics and geometry. The setting we consider is we're given a set system on a base set of n elements, and we have m sets, so m is at most 2 to the n. And we look at colorings of the base set of elements by either blue or red or plus or minus 1. And we're interested in coloring the base set so that each of the sets in our system is as balanced as possible. And the way that we're going to quantify that is this discrepancy quantity. So for any fixed coloring, the discrepancy of that coloring will be the maximum imbalance of any of the sets in our system, and we want to choose the coloring so that this maximum imbalance is as small as possible. And so we end up with this min-max problem. And here's a small example with a very simple set system. And we can generalize this to a linear algebraic formulation called matrix discrepancy, where we instead ask if we're given a matrix in Rm by n, then we want to find a vector of signs so that the vector Ax has minimal maximum norm. And if you note that if you take the matrix to be the incidence matrix of a set system with 0, 1 entries, then this exactly recovers the combinatorial formulation of the problem, but in general it's a much richer geometric problem and algebraic problem. So what does this have to do with quantization? Well, we can formulate our problem using kind of a discrepancy theory type language. So we're going to be given a neural network with a pre-trained weight vector W and Rn. We're given a data distribution on Rd with m samples from the distribution, where we again assume that m is much, much smaller than n, which is the number of parameters of our model. We're given our loss function, quantization grid, which we'll keep fixed. And as I said, our algorithm will be agnostic to this grid. And our goal is going to be to find quantized weights in the grid so that the loss function remains unchanged, essentially for both the samples that were originally given and then also an expectation for samples drawn from our data distribution. So we note empirically that the error in the loss function after quantization is very well approximated by this first-order Taylor series approximation. And so this is the formulation that allows us to make a discrepancy theory-based observation. So we can define a matrix where the ith row is given by the gradient evaluated at the ith sample. And then a simple observation shows us that minimizing the empirical error is equivalent to solving this discrepancy-looking problem after we reparameterize the weights of the network. And so this is the problem that we're going to solve. And there's a nice trick that's often used in discrepancy theory for dimension reduction. So that's what I'm going to introduce here, and this is the basis of our algorithm.
A quick clarification, what does y correspond to here?
So y is a reparameterized version of the original weights. So basically, I'm using x and y to be the scaling between 0 and 1 rounding up or down to the points in the quantization grid. Yeah, I glossed that under the
Thank you.
over here. And so our first goal is going to be to approximately solve this minimization problem. By approximately, I mean that I'm okay leaving a few of the coordinates unrounded to 0 or 1. And the way that we can do this using geometry is we can define this affine space where mx is equal to my. And this lies in an n-dimensional space. We look at the n-dimensional hypercube, and we intersect this affine space with the cube. And this defines a most n minus m dimensional polytope. And it's a well-known fact from linear programming, for example, that any vertex of this polytope has at most m non-integer coordinates and will give empirical error 0 because of the definition of the matrix M. And so because M is going to be much, much smaller than n in our applications, we can just round the last few remaining coordinates and not worry about the error that we incur there because it'll be quite small. But we note that while any vertex will give empirical error 0, most vertices will not generalize well. And so we need our algorithm to do something clever and not just pick an arbitrary vertex. And so the assumption that we make that will guarantee generalization is this low rank assumption, which I don't want to go into the details too much, but essentially we assume that a particular matrix that we're interested in has polynomially decaying eigenvalues, which we validate experimentally. And so the main theoretical result that we show is that we only need polynomially many n log n over epsilon samples in order to show a bound of epsilon on the generalization error, and we'll be able to round at least n minus m of the weights. So we leave very few weights unrounded. So unfortunately, the algorithm that we base this on from discrepancy theory is infeasible in practice because we would need to compute and store the gradients, which would be very expensive. So our algorithm uses a more practical approach, which, to very quickly sketch the details, it minimizes using projected stochastic gradient descent these two balanced terms, one of which keeps it close to a particular polytope that we're interested in, and the other minimizes a linear function to find a vertex that's close to the original set of quantized weights. And so to end, I just wanted to mention our experimental results for this practical algorithm. We run on 2 different models over a variety of tasks. We look at 2 different types of quantization schemes. And the key result is that our algorithm shows significant improvements over GPTQ and round to nearest for both of these models over a range of benchmarks. So here I highlight one particular level of quantization for a particular task. But in general, we see over both models and over a range of tasks at different levels of quantization that we get improved results. Yeah, that's all I wanted to say. Thank you.
Thanks for the great talk. Any questions from the audience? Okay, I think we'll move on to the next speaker in that case. Thanks again for the nice talk.
Yeah, one needed. Thanks.
The next presentation is by Francesco Camilli on information theoretic reduction of deep neural networks to linear models and the over-parameterized proportional regime.
Thanks a lot for the introduction. This is a joint work with Dr. Tieplova, Barbier, and Bergamin. And our work revolves around the problem of learning a target function that comes in the form of a deep neural network, which is feed-forward and fully connected, with an arbitrary but finite, with respect to the number of units and the size of the layers, number of hidden layers. So assuming that there is an underlying data generation process in the form of a neural network is a rather popular hypothesis among theoreticians, as usually it yields a good theoretical playground, and if you're lucky enough in this kind of settings, you can also give a satisfactory explanation to some phenomena that you observe in more empirical settings. And as we do here, sometimes you can also establish some theoretical benchmarks for the performance of learning such target functions. So very quickly about the teacher or the target function that generates the data. As I said, it's a fully connected feed-forward neural network. The inputs will be denoted by X. In the following, I collect all the parameters of the network in this theta star here. This X mu L that you see on the bottom is defining the standard forward pass operation with the activation function phi that will be taken to be, let's say, odd and regular enough. And then the last post-activation is projected onto a lower dimensional space by means of this V star, the readout weights. So the labels, y denoted by y, instead can be, in general, also a stochastic function of this last low-dimensional projection. So they are drawn from this P out. And once the teacher has produced enough input-output couples as examples, we can form this training data set, calligraphic D. And let's say, in order to obtain a theoretical benchmark, a highly relevant setting, especially from the information theory point of view, is the Bayes optimal one, where one assumes that there is a student learning this correspondence set by the teacher that is a neural network itself, and it has an architecture that is fully matching that of the teacher. By this, I mean that the student is aware of everything about the generating process of the data except the realization of the weights of the teacher themselves. As a consequence, the student has access to the Bayes posterior over the teacher network weights, and it can produce this Bayes optimal label predictor that you see here, this y hat BO, that is a posteriori average over the output of the network given the training set. And this is the label predicted for a new unseen input, bold X here, that is not present in the training set. Provably, and this is the theoretical benchmark we are going after, the Bayes optimal student achieves the best generalization error, meaning that it predicts the best possible label, okay, for an unseen output. The problem is that computing this calligraphic E as it is written in this slide, it's almost impossible, especially if the networks are rather wide, because it involves very high dimensional averages. So the whole point of our approach is to identify some scaling regimes in which hopefully this quantity reduces to something computable by means of low dimensional averages and few other parameters. And the regime one of the most popular regimes, which is also an overparameterized one as discussed yesterday by Bach, is the proportional regime, where the sizes of the layers labeled by these DLs are going to infinity, they're diverging, proportionally to the number of training samples in the dataset D. This is, as I said, an overparameterized regime because if you call D, let's say, the size of the smallest layer, then the number of trainable parameters is roughly D squared, which is in the scaling regime much, much bigger than the number of data at disposal. So as intuition may suggest, in this data scarcity regime, the student has vanishing information about the inner weights of the teacher because there are too many. So the best thing it can do is adjusting only the readout weights that are fewer, okay, to fit the input-output correspondence set by the teacher, and this yields an effectively linearized model, so it ends up behaving as a generalized linear model. This is explained in very broad terms, but in the base optimal setting, a more precise meaning, at least at a conjectural level, of this phenomenon was given by Puig, Zacala, and Zdebrova in their ICML from 2023, and they achieved this linearization by means of these Gaussian equivalence principles. Gaussian equivalence principles basically allow you, to a certain extent, to be established, to replace the nonlinearities that are due to the presence of hidden layers by equivalently linear model, one by one. You pay a price for this, and this price is the introduction of this extra noise that you see in the red box. It's this psi mu star. And then there are these two coefficients, rho and epsilon, that are related to the Hermite coefficients of the activation function phi, and they are the only memory of the nonlinearity that was there before in the model. And okay, so to what extent these Gaussian equivalence principles are applicable in the base optimal setting in this proportional regime? To our best knowledge, it was not clear before, so this is basically what we proved. We proved their conjecture and did slightly more than that. We went a bit beyond. The proof of the conjecture comes in form of this layer reduction theorem, which states the following. So if you take white Gaussian inputs and you have a Gaussian prior over the weights of the teacher network, then, taking an odd activation function that is regular enough, what you can prove is that the mutual information, which is the relevant quantity from information theory point of view, the mutual information between the teacher's weights and the data set it has produced to train the student can be actually computed with that of another teacher that has one layer less. The last area in particular can be smartly integrated away and replaced by an equivalent linear layer, as you see here in the y mu L minus 1 that are the labels that would be produced by this reduced teacher. This rho L and epsilon L are two coefficients that are perfectly analogous to the ones you have seen in the previous slide. And they are the endpoints of these recursions that you see on the top of the blue box here. So this theorem identifies a natural scaling, which is the one for which this big O on the right-hand side of this control vanishes. And it clearly covers the proportional regime, because if n is proportional to d, this vanishes thanks to the 1 over square root d factor at the end. And it does even a little bit more. We can take n up to d to the 3/2 minus something, let's say, minus delta. This has an important corollary, because once you have reduced a layer, you can keep going on. So you can integrate them out one after the other in a recursive way. And each time you do, you produce an offspring of coefficients that reweight signal and noise, as you can see here. And these eta 0 and gamma 0 that you see in the let's say, fully reduced teacher labels y mu 0 are the last descendants of this offspring of coefficients that you produce, and they can be re-expressed if you sit down with pen and paper in terms of sigma L, rho L, and epsilon L of this recursion on top. The good thing about this theorem and this corollary is that the mutual information for a model which has no hidden layers, okay, when you have reduced them all, is that this mutual information is computed already in the literature. This is due to Barbier, Zacala, Zdebrova, Miolan, Macri, and I apologize if I forgot someone, because it's a generalized linear model. And the good thing is also that the generalization error experiences the same reduction. So we can also compute the generalization error for the learning problem of the target function neural network with an arbitrary number of layers in terms of the generalized linear model one. So just a hint of the proof, the core idea is a Guerra-Toninelli type of interpolation, which is very popular in spin-glass theory. What we do is to construct an interpolating data set and an interpolating teacher by means of this continuous parameter t that ranges from 0 to 1. So at t equals 0, these labels are distributed as the ones of the original model. At t equals 1, instead, you have completely forgotten about the nonlinearity. And in the middle, if you control derivatives of the interpolating mutual information, which will also depend on d, with respect to t, and you prove they are small, basically, you have proved our result. This is the main idea. And to prove the vanishing of all the remainders that you get, you need these two moment controls. The first one is clarifying the meaning of the sigma L. That is nothing but the square norm of the post-activation at layer L divided by the number of its components, so this is a concentration result, as the second one. Second one is also interesting in my opinion because it's a quasi-orthogonality preservation property by the forward pass. I would like just to conclude with this last slide with an open challenge, and then I'm done. So we have evidence instead that when n, the number of data disposal, is proportional or a suitable fraction of the number of trainable parameters, this linearization does not occur anymore, and the application of this Gaussian equivalence principles breaks down. We have conjectured a formula together with colleagues in this paper that appeared on arXiv recently. There is also a nice paper by Antoine Maillard, Yizuk Su, that they are presenting this week about a related problem. They prove this formula in a specific setting, but we think that, let's say, one has to work way further before getting a proof of the full conjecture that we have. Thanks a lot.
Thanks for the nice talk. Questions? Okay, in the interest of time, we'll move on to the next speaker. Talk will be by Sholem Shesman on the late-stage training dynamics of SGD and homogeneous neural networks.
Yeah, so good morning to everyone. My name is Sholem, I'm from Télécom Sud Paris, and this is a joint work with my friend Nicolas, who is at Paris also at Université Paris-Est. And so to start with a small introduction that we're interested in the problem of empirical mean minimization. So you have some training data, some loss function, and you try to predict some labels by a neural network. And typically, like the motivation is that modern neural networks, as you know, are typically over-parameterized, which means that there are much more dimension of the parameters, much larger than the number of data points, which means that typically we will have many interpolating solutions, so many points W stars that minimize the loss, that put the loss to 0. However, often, empirically, we observe that the points that it's found by simple algorithms such as gradient descent or stochastic gradient descent, often they have good generalization properties. So it has led to something that is in the community is called the implicit bias hypothesis. So we are biased by the fact that we are choosing, there is an algorithm that chooses an interpolation point. And so this talk is like a small humble contribution in this direction. So let's dive a bit deeper to the model. So I'm interested in classification with homogeneous neural network. So classification means that the labels are, you have two labels, -1, 1. And you try to predict this label by a neural network. So you try, your neural network phi will try to predict the sign. Its sign will predict the label. And now you have the sign prediction, which is the multiplication of the label by the neural network. And the goal is to have this thing bigger than 0. If it's bigger than 0, then you are good. If it's smaller than 0, then you are wrong. Okay, but we are not looking at any neural network. We are looking at neural network first. First thing, it's a neural network without biases. So there are only weight matrices. There are no B. And second thing, we are looking at neural networks with homogeneous activation functions. So for example, ReLU or Leaky-ReLU, they're commonly used in practice. And with this, because of the structure that I impose on the network, actually the whole network or the whole sign prediction is positively homogeneous, meaning that if you multiply your weights by some positive scalar lambda, the output will be multiplied by lambda in the power of L. Okay, so yeah, and I will concentrate on the talk on the loss that we will take. It will be exponential logistic, the commonly used. As I told you, the sign prediction will be positively homogeneous, and we can make two observations. First, that, okay, I told you that the classification depends on the sign on P, and we want that P is greater than 0. But since the neural network is positively homogeneous, actually this sign doesn't depend on the whole W, but only on the direction. So if you define U is W on the norm W, this is completely characterized if you're wrong or not wrong. So this is because it's homogeneous, so the sign depends only on the direction. Okay, second observation, imagine that you are in the context where the data is separable, which means that there is a parameter that correctly classifies all of the data, which from another point of view means that what we call the margin, so the minimum of the different pi I, so different sign prediction, is strictly greater than 0, which means that you classified correctly all of your data set. Then, due to the structure of the neural network, and mostly the fact that you are losing like a decreasing loss, exponential logistic, if you find such a parameter that separates the data, and you multiply it by lambda, which is greater than 1, then actually you will decrease the loss. Which means that, okay, if you want, we as optimizers, at least, we want to minimize the loss, the best way you can do is you find the parameters that separate the data, if you have some, then you just start to increasing the norm to infinity, and with that thing, but the loss will go to 0, and you finished. You optimize your loss, and you cannot do better. But if you look at the first observation, like I told you, that the classification depends only on the direction. So the question is, the natural question is, what happens with some kind of optimal direction? And yeah, this is what we'll be looking at. So, of course, we are not the first one looking at this settings. There is many of different works that I list here, and there are many of them that are cited in the paper. But mostly, we are trying to generalize the work of Liu and Li that considers the setting, and they were considering not an algorithm, but the subgradient flow, so the continuous time approximation of subgradient descent. So you're looking at the trajectory of the subgradient flow. And they have, like, one of their main theorem tells that if you look at the trajectory, that at some point, this trajectory correctly classifies the data, which means that the margin is strictly positive, then actually when you look, okay, the W will go to infinity, as I told you, but when you're looking at the direction on WT on norm, you will find that any limit point of this direction will be what they call a rescaled KKT point of the max margin problem. So it means that you take any limit point U star of the directions, there is some lambda, such that if you multiply it, it is a solution of this constraint optimization problem when you minimize the norm, constrained to the fact that the margin is strictly greater than 1. And so this is some implicit bias, because like at the beginning, when you look at the problem, you don't see the margin appear, but when you look at the limit of the direction, you see that, okay, the direction is some kind of critical point of the max margin problem. Okay, so they have the results for subgradient flows. They have also similar results for smooth gradient descent. But smooth gradient descent, it means it's an algorithm, but it means that you cannot have reduce or linear reduce. And they don't have stochasticity. So the goal of our paper was to generalize this results to stochastic subgradient descent, so stochastic and non-smooth. So yeah, and so this is the algorithms that we are looking to, and the assumptions are more or less the same. And actually, we have more or less the same results. So it's it's almost the same results. Just we have one thing: all of the results are are holding conditional on event. So this is event E. So the algorithm is stochastic, so it's a probabilistic event. On the fact that this event E tells us that asymptotically, on the limit, the direction correctly classifies the data set. So M of UK is strictly greater than 0. But if we are on this event, actually the result is exactly the same. So almost surely on this event, any limit point of the direction will be a rescaled version of a KKT point of the max margin problem. Okay, so this is nice, but maybe I think that the proof is nicer, so it's really not hard. And I think I just want to give you a key idea. You just have to write down the dynamic and then to know some things, and after that, the proof is trivial. So actually, what we do, we just write down the dynamic of UK. And we found, in short, we find out that UK can be seen as a stochastic approximation or Euler discretization of some kind of subgradient flow. So this is the dynamic that you write down, but just by some Taylor expansion, basic. And what you see that UK plus 1 is equal to UK plus some things. And the first thing is that you have a new step size parameter, bar gamma k. So at the beginning, you had constant step size algorithm. But actually, after irreparable initialization and the fact that WK goes to infinity, when WK goes to infinity, even at the constant step size, the direction will move slower and slower. So you have this parameter that goes to 0. Then you have some stochastic errors that come from stochasticity and from Taylor expansion. And finally, you have this JK, some vector, that you project on the transversal projection, so projection of the tangent space of the sphere. And when you look at it, you just find that when k goes to infinity, actually JK converges to some object, which is not a subgradient, but something, okay, thank you. Something that is known, it's called, like it was introduced by Bolt and Powell, like it's a general object, is a conservative set-valued field of the maximal margin problem. So it's not exactly a subgradient, but actually it behaves mostly as a subgradient. So with that, and mainly because of the fact that gamma bar goes to 0, you have this equation. It's a good approximation, stochastic approximation, of this subgradient flow projected on the sphere, differential inclusion. And actually, as soon as you have that, the proof is finished, because by standard results of stochastic approximation, Benaim and al., Davis and all, and different people, you see that this is, if you look at ds as a subgradient flow in the sphere, this thing will converge to ds critical points. And actually, by stochastic approximation results, UK will have the same behavior. And actually, these ds critical points, when you look at them, they are exactly the rescale KKT points of Liu and Li. So yeah, so just a brief summary. So we have like generalization of results of Liu and Li to the non-smooth and stochastic setting. I think it's interesting. It's not hard, but it's interesting. Like we have another point of view with another proof technique, stochastic approximation. I think like small comments which I found interesting is that actually we have convergence under constant step size. So usually when you do non-smooth stochastic subgradient descent or even just non-smooth, you need decreasing step size to show convergence. But because of the fact that actually WK goes to infinity, the effective step size goes to 0, which allows us to have true convergence. We have another interpretation of KKT points as ds critical points of some conservative fields. Actually, it's nice it naturally appears in the analysis because conservative fields were introduced to explain automatic backpropagation, but here it has nothing to do with automatic backpropagation. And I think the proof technique is quite general. Hopefully we didn't check, but I think it adapts to algorithm other than HGT, because you just need to look at the dynamic, look at the flow, and yeah, hope that everything works. And thank you.
Yeah.
Hey, nice talk. I wonder whether there is a chance to remove this condition that UK needs to converge to.
You mean like the event?
Yeah, the event.
Yeah, this is kind of a stability condition. So it's usually hard when you're looking at subgradient descent, even just normal subgradient descent on a smooth function. Even if you're in the neighborhood of critical points, it's hard to prove that you will remain in this neighborhood, even without stochasticity. Like in non-smooth, non-convex world, I said. What?
Sometimes you can do it.
Sometimes, but in non-smooth, non-convex, the only thing that I know is that maybe, and here I suspect that we could do it, that if the step size is small enough, then yeah, you will not go away. But here you don't have any descent lemma or anything that's controlling. It's like everything is.
And the other results that came before you.
Yeah. Yeah, but this is a gradient flow or smooth gradient descent. So subgradient flow, you have a decrease of the potential at any point. And the gradient descent also, you have a descent lemma. In non-smooth, I mean, it will be very good to have such results, but it will be kind of a revolution in non-smooth world. I mean, we don't have, usually non-smooth, non-convex settings, we don't have descent.
You know the short line kind of rescaling technique to get this stability?
Yeah.
Wouldn't that work?
Yeah, some kind of this thing might work, but we have to look if the rescaling goes to the good. You need to have some like coercivity or some kind of stability, or yeah, something like that. But it will also be, I think, for small step sizes and enough step sizes.
Yeah.
Yeah, something like that I suspect would work, but yeah, we need to check it.
Okay, any other questions? I had a quick one. Is there a scope for the stochastic approximation technique to be useful for like other loss functions such as the square loss? I mean, there's some other difficulties in the implicit bias that arise there, but I'm curious.
Yeah, I mean, the only things that you need, but it depends, everything depends on that, is are you able to write down some kind of dynamics that approximates some flow? So if you're able to do it, yes. Here we used a lot like the square loss. I mean, it's not square loss. We have logistic exponential.
Yeah. I mean,
yeah,
it seems like
usually,
where that mostly comes up is in the margin, the kind of the interpretation of everything in terms of margins, and that shows
here's
up
the margins because of sum of exponential. You normalize, so you have some kind of soft max, and soft max converges to the maximum, something like that. Yes, you need to look at case by case in some sense.
Okay, we have no other questions. Thanks again for the nice talk. We will next hear from Ishan Nichani, who will tell us about learning compositional functions with transformers.
Hi, everyone. My name is Ishan. I'm a final year PhD student at Princeton, and today I'll be talking about our paper, Learning Compositional Functions with Transformers from Easy to Hard Data. This project was joint work with this great set of collaborators, Zixuan, Alberto, Alex, Daniel, Jason, and Denny. So, the motivation for our talk is the multi-step reasoning capabilities of current language models. So as anyone who's interacted with an LLM probably realizes, LLMs are very good at solving complex tasks, which require combining multiple intermediate reasoning steps. Okay, what do I mean by this? Like one example is, say, in natural language. You might have a paragraph of a story, like John plays quarterback, the football game is on Sunday, on what day does John play? And an LLM needs to reason about, make deductive reasonings about this paragraph in order to output the correct answer. In other settings, such as coding or mathematics, a model needs to combine multiple intermediate steps in order to prove a result or write proper code. So these sort of practical reasoning tasks often require combining contextual information, i.e. information provided by the user in the prompt, with parametric knowledge, i.e. global facts that are not provided by the user and must be learned during pre-training. So in our natural language example, the contextual knowledge here will be the associations John maps to quarterback and football maps to Sunday. But in order to solve the task, the model needs to know that quarterback is a position in football. Likewise, in coding or mathematics, the contextual knowledge could be definitions or variable assignments, while the parametric knowledge might be which theorem to use or which function to call. So the goal of this work is to understand how LLMs learn to perform such multi-step or compositional reasoning. And specifically, what is a model for compositional reasoning with both contextual and parametric knowledge? How do transformers efficiently express such tasks? And most importantly, how can transformers learn such reasoning tasks via gradient-based training? So our main contributions are as follows. We first introduced the k-fold composition task and proved that there exists a log k depth transformer which can solve the task. And moreover, we proved that curriculum learning is both necessary and sufficient in order to learn the task via gradient-based training. Okay, so let me return back to this natural language example now spelled out in more detail. So the first observation is that we can formulate multi-step reasoning as function composition. Okay, so specifically, the input describes multiple functions. Here it describes one function sigma1, which maps from the set of names to the set of positions, and another function sigma2, which maps from the set of sports to the set of days. Okay, moreover, the input contains this starting index x, being John. The parametric knowledge is also a function. Here, it's the hidden function pi, which maps the set of positions to the set of sports. So the target function f sub pi that the model must compute takes as input these sigma1, sigma2, and x, and outputs this interleaved composition of functions evaluated at the starting index x. Okay, so given this motivation, we're going to define our k-fold composition task as follows. The parametric knowledge pi is going to be a tuple of k hidden permutations on the set of n elements. So here we're making the assumption that these functions are just bijective or permutations on n elements. And this is going to be fixed for the target function. The input will consist of sigma, which is a tuple of k input permutations, as well as a starting index x from 1 through n. And this will vary between the different examples. And the target function f pi takes as input some sigma and x and maps it to the following interleaved composition of permutations evaluated at the index x. So a nice diagram is here. So the red arrows correspond to the hidden permutations that are hidden, and the green arrows correspond to the input permutations that vary from input to input. And so the thing I want to emphasize here is that this hidden pi defines a function class, as we vary pi over all possible tuples of k permutations. And as such, since we have this function class, we can reason about like hardness of learning, et cetera. Moreover, we're going to encode our input using n tokens for each permutation. And as such, the total sequence length that gets passed into the transformer will be k times n. Lastly, I want to note that our task resembles other sort of compositional or multi-step reasoning tasks in the literature, such as automata simulation or the k-hop induction head. Our model is going to be a multi-layer transformer. So I guess the key building block is a self-attention head, which takes as input a length t sequence of d-dimensional embeddings and outputs a length t sequence of d-dimensional embeddings. It's parametrized by these key query and output value matrices, such that each output is a convex combination of these values, where the weights in this convex combination are computed via this softmax function. A multi-layer transformer is just going to compose multiple of these self-attention heads in series. So we're going to start out with a sequence of t tokens. We're going to have some embedding function phi that maps these to vectors in RD. And then each layer is just going to be a self-attention head with a residual connection. And then lastly, we're going to have a readout layer that maps the final layer to an n-dimensional output at each position. So our first question is, can transformers efficiently compute this function f sub pi? And the answer here is yes, that O of log k layers suffice. Okay, so formally we show that there exists some embedding function phi, such that for any hidden permutations pi, there exists a log k plus 1 depth transformer which can exactly express the k-fold composition task. So if you're familiar with some of the literature on transformer expressivity, this isn't particularly surprising. And a lot of prior works have shown that transformers can efficiently perform parallelizable computations. So our construction here similarly exploits such parallelism by just building a binary tree. So we have as inputs our k permutations. And what the first layer is going to do is going to encode the hidden pi I and compute these permutations for each I, sigma I composed with pi I. It does this by encoding the pi I in the key query matrices of each of the first layer, the first self-attention layer. Next, the second layer is going to compose adjacent sigma I pi I with sigma I plus 1 pi I plus 1 to get the following hop2 function. The third layer is then going to compose adjacent hop2 functions to get a hop4 function. And this procedure continues such that after log k plus 1 layers, we've exactly computed the k-fold composition. So we've shown that transformers can express the k-fold composition. What about learnability via SGD? And we're going to specifically consider learnability with respect to the learning with respect to the uniform distribution over sigma and x. It turns out here that it's hard, and specifically we prove a statistical query lower bound against learning the k-fold composition f sub pi. So the statistical query model is as follows. The learner gets to specify some set of queries and a tolerance tau, and some SQ oracle gets to respond with a noisy estimate to the population values of these queries. So anything within tau of the correct expectation. And this SQ model has been used, describes a lot of common algorithms such as gradient descent and is a useful proxy for the computational hardness of learning. So formally, we prove the following. We show that any SQ learner must either make n to the omega k queries or use tolerance tau n to the minus omega k. So as I mentioned before, gradient descent is an SQ algorithm. And one common concentration heuristic is that the tolerance tau scales like 1 over square root n, where n is the batch size. So using this heuristic, that tells us that in order to learn this k-fold composition task, SGD either requires exponential compute or sample size. Our proof relies on standard SQ arguments by constructing a large subset of functions which are nearly orthogonal. So while trying to learn the k-fold composition directly is computationally hard, we next show that curriculum learning, i.e. training on easier examples, can lead to efficient learning. Our construction motivates a natural curriculum. So recall that we defined this hop R function to be the composition of R consecutive permutations. We saw that in the construction, the Lth layer would compute the hop 2 to the L minus 1 function. So as such, we consider the following curriculum learning algorithm, where in the Lth stage, we consider the loss with labels with hop 2 to the L minus 1 data as labels, and take a single gradient step on all of the key query matrices. So we show that this curriculum learning algorithm succeeds with sample size which is polynomial in both k and n. So the takeaway here is that while just naively trying to learn from the k-fold composition directly requires exponentially many samples, curriculum learning succeeds in polynomially many samples. Altogether, this shows that easy examples or intermediate supervision is essential for learning complex tasks. Beyond just curriculum learning, we also consider a different setting where instead of training on examples of increasing difficulty, we train on a mixture of examples of 2 to the L minus 1 hop data all at the same time. And here we show that the transformer succeeds in learning with polynomial sample complexity as well. Finally, we include some simulations where the left two plots are in this idealized theoretical setting, and the rightmost plot is a slightly more realistic transformer with trainable embeddings, MLPs, layer norm, et cetera. And generally, we see the same phenomenology that trying to learn from, say, or k-fold data directly is hard, whereas either curriculum or mixed training can succeed more efficiently. So a couple remarks. So the first is that the k-fold composition here is exhibiting a statistical computational gap. So the information theoretic sample complexity is just kn log n. And this is just the log cardinality of the function class. On the other hand, a computationally efficient sklearner requires n to the omega k samples. This mirrors the k-sparse parity problem, which has been commonly studied in deep learning theory, and which requires d to the k samples or compute to learn. However, one key difference between our k-fold composition and k-sparse parity is that k-parity is expressible by a one-layer transformer, whereas the k-fold composition fundamentally requires this larger depth, making it fundamentally a compositional task. So to conclude, there's been a lot of prior work on the expressivity of transformers, but I guess the tasks that are expressible by transformers are not necessarily efficiently learnable via gradient descent. And whether or not these tasks are learnable via GD really depends a lot on the underlying data distribution. So we saw that training on the k-fold data directly was hard, whereas training on either a curriculum or mixture was easy. So some future directions that I think are really interesting are trying to either understand upper bounds, which are i.e. learning guarantees, or lower bounds, characterizing the complexity of GD for a more general set of compositional or algorithmic tasks. And I think this could be of a lot of interest to the deep learning theory community to try to think about how can we go beyond some of these toy tasks such as parity or polynomials and think about more discrete tasks that more closely resemble what we may encounter in, say, like language modeling. So thanks so much for listening, and please check out our paper if you have any more questions.
For the nice talk, questions?
Thank you. Very nice talk. Yeah, the question is, how do you prove that when you're using the curriculum, the difficulties are overcoming? I mean, it seems that I guess there could be some interference when you're trying to teach later more complex functions, and the information that's already stored somehow is not destroyed, despite the fact that there is that interference. So how does that happen? Like, what proof techniques do you use to deal with that?
Yeah, so that's a good question. So I guess in the curriculum learning algorithm, I glossed over the details here, but we specifically look at training the key query matrices. And I guess the proof sketch is that when you're training in the Lth stage, stages 1 through L minus 1 have already learned, and these key query matrices are very big, so they've kind of completely saturated the softmax. And so in the Lth stage, just the Lth key query matrix gets updated and grows to converge to the correct thing. And I guess in this specific setting, we don't have this problem of interference because in order to go from, say, 2 to the L minus 1 to 2 to the L, the only thing that needs to change is the Lth layer needs to grow, whereas all the previous layers are doing like the same computation regardless of whether you're computing the 2 to the L minus 1 hop or the 2 to the L hop. So I guess curriculum learning is like very natural for this problem because like if you were to just like throw away all the later layers of the transformer, this is exactly kind of computing what you want, yeah, like the simpler task that you want.
Thanks. Really nice. I have a question. Do you know if there's a gap between the curriculum and the mixture? Maybe you said that and I missed it. In terms of the sample complexity you need, if you use a curriculum and I just use the mixture.
Yeah. So in this case, I don't think we didn't observe any gap. I guess in the mixture setting, it kind of mimics this the curriculum where. When you the first step of gradient descent, only like the 1 hop data matters, and then the second step, only the 2 hop data matters. But since we're doing like powers of 2, this I guess would only affect the sample complexity by like a factor of log k. Maybe I think the sample complexity we get by no means it's like tight or like this is like the correct polynomial. So there could be a gap, but I guess it's not something that we observed.
Yeah, thanks.
Thank you. So my question is. So in your analysis, how did you model the interface between text sequence and compositional functions? In other words, what is X in your analysis here?
Yeah, so I guess that's a good point. The X is going to be like an index from 1 through n, and then I guess we kind of hard code reading out from like the correct output corresponding to X. So the output of the transformer is going to be like a sequence. And then we just say like X indexes into like the correct point of the output, at least for the theoretical results. If you considered X actually being one of the input tokens, then you could do this with like one more self-attention layer. But just for like ease of doing the gradient descent analysis, we just assumed that like X told us exactly which position to read out from.
Okay, I see. Thank you.
Yeah.
Thank the speaker again, and we will.
Just take a second to do.
Okay, we'll next hear from Arif Karamdai on low-rank fine-tuning lies between lazy training and feature learning.
Hello everyone. I'm an incoming PhD student at MIT, and this is work I did during my undergrad jointly with Sitan Chan. I'm going to talk about how we analyze low-rank fine-tuning in the deep learning theory setting. So the motivation for our work is, as you might all be familiar with, there are these models that are pre-trained on huge amounts of data, but then they can be fine-tuned to specialize on certain tasks with significantly less amount of compute. And even though there's this huge empirical success, and there's all the works that focus on learning, let's say like 2-layer networks or similar functions, there isn't as much work on post-training, and our understanding of post-training from a rigorous perspective is still limited. And there are some related works though. It's relevant for our talk, and especially there are some works on feature learning that focus on learning low-dimensional functions. And here, we have some complexity measures such as like the information exponent for generalized linear models, which generalize to the leap exponent for multi-index models, which kind of here there's some property of the nonlinearity of your data that comes up in the exponent of the dimension dependence. But even though you could go beyond these using some tricks to go beyond CSQ algorithms, these have been recently generalized to more general statistical query algorithms. And on the other hand, if you don't care about feature learning, but just care about optimization, you could also say, well, I want to operate in the kernel regime, maybe in the very highly over parameterized setting where you can approximate the network with its linearization around the initialization. And here, in particular, the work relevant to us is previous work has shown that, empirically and also some theoretical result that if the downstream task is natural for a base model, you can have kernel behavior. But this kernel approximation will break down eventually as you go beyond the few-shot setting where you're only using few samples. And so the question is, can we understand fine-tuning rigorously beyond this very few-shot training regime? And for that, we consider the setup where, the two-layer networks are well studied, so we consider this natural setup where, let's say, you have a two-layer base network with, feature dimension D and the width K, and you have these weights that are normalized, and you know this base model. And the goal is to fine-tune on some distribution given with this teacher model where X is Gaussian and Y is labeled by this teacher network, which is also a two-layer network. A priori, if you don't make any assumptions on the WI for the target model, this isn't very meaningful because what's the relation between your base model and the target model? So here, to make some natural assumption on the target function, we consider this LoRa algorithm, which is very highly successful in practice. And people have shown that instead of fully training the mate matrices, you could train low-rank perturbations, and this does well in many practical tasks that we care about. And so a natural idea is that maybe the target model should be some low-rank perturbation of your base model. And here, for theory purposes, we consider the setting where the rank is 1, so that the target weights are a rank 1 perturbation. So you have this, weight W, and you add this rank 1 spike, and we normalize it such that, U and C, the vectors controlling the matrix direction, are normalized so that this psi parameter gives you how big the perturbation is. And we also, re-normalize it so it's still like a two-layer network with normalized weights. And, the idea is that we have the scaling parameter. And if the scale parameter is small, then, you're very close to the base model. So you're in the lazy training regime where linearized networks do well. But if the scale parameter is very large, then it's like the base model isn't very helpful, and you're learning this rank 1 function from scratch. So this is sort of like the generalized linear model setting. So the question is, what is in the intermediate regime where we have some non-trivial fine-tuning? And in fact, if you look at the simulations, you can see that linearized networks will fail in this intermediate regime, but as you also increase the scaling parameter, the problem gets harder. So this is not as hard as feature learning, but also linearized models don't really explain this regime. So, and I hope by this point the setup makes sense, and you think this is an interesting thing to study. So I'm going to now talk about what we can prove in this setting. So the first style of result we have is that we make certain assumptions on the weights, and we use online stochastic gradient descent to get this convergence result to characterize the iteration complexity and also the sample complexity of low-rank fine-tuning. And here, we consider two scaling regimes. And in the first scaling regime, this is the spectrally comparable regime where the perturbation is spectrally comparable to the base network weights. And here, we show that to recover the ground truth direction, it suffices to have order dk cubed or epsilon to the 4th number of iterations, and we have a similar result for the larger perturbation setting where the perturbation is comparable to the weight matrix in Frobenius norm. But in particular, there's no exponential dependence on sigma here, as opposed to the results for feature learning where there's some quantity about the activation that shows up in the exponent of the dimension. So a question then is is it easier to fine-tune in some settings, and can we indeed show a rigorous separation? And the question is can having the base model actually help you rigorously? And for this we say yes, and we show the following result. For a given natural number p, what we can construct is a class of base models and a class of low-rank perturbations such that if you don't have the base model, it's hard to learn the target model with a CSQ algorithm. In particular, you need this exponential dependence on p. And if you have the base model, then you can do online stochastic gradient descent, which is still a CSQ algorithm, but we have the base model now. And you can learn in order dk squared iterations. And in fact, this could be generalized to general statistical query algorithms using some recent results. And the proof technique we use is to analyze the dynamics essentially and show that the estimate converges to the ground truth. And to simplify the analysis, we recall we had C and U as vectors, and we fixed C, and we trained U, and we randomly initialized C. And we use a drift martingale decomposition similar to previous work on single index and multi-index models. And our assumptions allow us to reduce the population dynamics to this low-dimensional quantity that only depends on the overlap between the ground truth and your estimate, according to some very complicated nonlinearity. So this is where we significantly diverge from previous work in that the nonlinearity effect controlling dynamics is significantly more complicated and depends on these moment tensors, which are random because of the random initialization. And there's also these mini quantities that a priori is not clear what their magnitudes should be. But the goal is to show that this quantity is nice and lower bounded in the sense that you get sufficient signal from the population gradient so that the noise in the gradients is not too bad in the long run. And for this, I'll briefly say the kind of technique we use to show that the population gradient term is not too small is that we show it's anti-concentrated around the origin. And to show this, we initialize the C in a discrete way to make the analysis simpler. But for that, we need to then show that the quantity as a function of the C is low influence so that under the randomness of the C, you can use some central limit theorem type argument and then use the anti-concentration of Gaussian polynomials. But to recap, we modeled fine-tuning as a low-rank adaptation problem of two-layer networks, which is kind of the setting that's been studied in learning theory. And our analysis suggests that there isn't this significant activation dependence that it shows up in the exponent, and you can also verify this in simulation. And this regime sort of lies between kernels and feature learning. So there's this intermediate regime that's interesting to study where you can say something meaningful about fine-tuning. And we can also give concrete example of a separation in the form of base networks and perturbations that show a separation. And I think there are many interesting follow-up directions to this. This is, I think, a first step in this direction that we took, but there are a lot of empirical phenomena to explore in this direction. For instance, what happens as you make the perturbation larger. And also, a theory question is, if I give you a base model, what are the class of models you can learn efficiently from this? Because then you can say something about how useful the base model is. Because if you can learn a very large class of functions from a given base model, then that says something about the usefulness of the base model. And there's also what are the transitions as you make the perturbation larger, or maybe change the rank of the perturbation that go from fine-tuning to, let's say, feature learning. And we consider stochastic gradient descent in this work, but I think that you might be able to get more general results than what we have if you consider more general classes of algorithms. So I think that to understand the complexity of this problem, I think it's also worthwhile to consider other algorithms, such as tensor decomposition. And yeah, thanks everyone for listening.
Thanks for the nice talk. Any questions?
So does any of this generalize to higher dimensional subspaces, instead of just having rank 1, or was this just for the talk that you described rank 1?
Yeah, so we currently don't have a generalization to greater than rank 1, which, there's the reason for it is, I think there's a significant leap to go from rank 1 to rank 2, similar to going from, let's say, a single index model to a multi-index model. But I think that's an interesting direction to explore.
I had a very quick one. So in your framework, you're assuming that the original sort of teacher model is exactly the same as the base model. What happens if there is misspecification over there and then you add a perturbation? Is that an interesting regime to study?
Yeah, so I think it's interesting. So, the reason we assume that you could learn exactly is, you sort of need some relation between the base model and the target model. I guess, one way of saying that is in practice, we have observed that low rank perturbations can learn interesting stuff, even with rank 1. But you could maybe say there's some misspecification, but then you need to specify like what that misspecification is.
I'm saying like bounded, but maybe, for example, maybe the base model, maybe the pre-trained model has learned a slightly different subspace that's not exactly corresponding to what like supposing there's some transfer between the pre-trained model and the new task that's been given. Like, I guess that was the motivation for this.
Yeah, so, it doesn't have to learn the exact subspace, even in this case, because, if the perturbation is, let's say, orthogonal, then you could have, like, a new subspace added, but it's still, there's some relation between the two, yeah.
Okay, let's thank the speaker again. For the last talk of this session, we'll have Margaret Glasgow telling us about propagation of chaos in mean field two-layer neural networks beyond finite time horizon.
Okay, hi everyone, I'm Margaret, and I'm going to be talking about propagation of chaos in mean field two-layer neural networks beyond finite time horizon, which is a slight modification of the normal title that appears in the whole thing right now. And this is based on joint work with Denny Wu and Joan Bruno, who are at Flatiron and NYU, respectively. And this work was conducted at the Simons Institute, and I'm now a postdoc at MIT. So this is a talk about mean field neural networks, which are the limit obtained when you have really wide two-layer neural networks whose width goes to infinity. And as Francis Bach introduced a few days ago, this limit also occurs when you scale the initialization of all the parameters in the two-layer neural network in a certain way. So the main focus of this work is, does the behavior of a reasonably wide two-layer neural network, this one on the left, well approximate the behavior of an infinite width neural network? So why do we care about these very wide or infinite width neural networks? Sorry, I forgot to say one thing, which is that the name of this phenomenon, when this approximation to the infinite width neural network holds, is called propagation of chaos, which is a larger phenomenon in statistical physics, but for now you just need to know that it's this approximation holding. So why do we care about this? Well, really wide neural networks are relevant in the real world for a couple reasons. First is that we've seen from a lot of scaling laws that have appeared in the literature recently that large width neural networks are required to achieve small loss. So here we can see that there's a polynomial decay with the number of parameters of the loss with the number of parameters, and typically the width scales something like the square root of the number of parameters. Another reason we might care about infinite width neural networks is that it turns out that understanding neural networks in the infinite width limit can help us determine how to scale hyperparameters in very wide models that are not actually infinite width but have finite width. So for example, Greg Yang showed in a series of work that there are certain parameters like the learning rate or the scaling of the output layers of the neural networks that if we can find the optimum of that hyperparameter at a smaller width, that'll actually extend to the optimum of that parameter when we scale the width to be even bigger. So this allows us to choose the optimal hyperparameters for neural networks on smaller ones without having to do that hyperparameter search on the final largest width neural networks that we will use. Another reason why we might care about infinite width neural networks is that it's possible to derive in a lot of problems very elegant training dynamics for them. So this idea comes from modeling the network as a continuous distribution on the neurons. So for a width m neural network, when m is finite, if we want to track the dynamics of this neural network, we have to track, if the input dimension is d, then we need to track d times m different parameters and how they evolve in time. However, if the width goes to infinity, we can think of the neurons as being a distribution over the subspace in RD. So here I've modeled the neurons as a density row, and we can think of the output of the network as the expectation over those neurons of the activation applied to the input dotted with the neuron. And in many problems that we might care about, if there are a lot of symmetries in the data distribution or in the target distribution, then tracking the dynamics of this density as we do gradient descent on the neural network often reduces to a simpler low-dimensional dynamic. So for example, in this picture, you can see that there are certain symmetries in this distribution. It's rotationally invariant here. And as the gradient descent evolves the network, these symmetries will continue to hold. And so this dynamics becomes simpler to track. OK, so let's go back to our main question. Does the behavior of a reasonably wide neural network well approximate the infinite width neural network? And to make this a little bit more precise, in a lot of learning problems that we care about today, the input dimension of the neural network is actually going to grow to infinity, perhaps at some slow rate, because the problems we're dealing with are very large, and we might want to understand how big this width has to be in terms of the input dimension d. So a more refined version of this question is, does the behavior of a polynomially wide neural network, where the polynomial is in d, well approximate the infinite width neural network? So a lot of prior works has actually told us that for short training times, the answer to this question is yes. We can approximate the polynomial width neural network by an infinite width neural network. So just a few highlights of works in this line. So if the input dimension is d and t is the total training time that we train our network with gradient descent for, then Song Mei and his co-authors established that if d and t are both constant order, then as long as the width goes to infinity at some rate, you will have a close approximation that decays with the width between the infinite width neural network and the finite width neural network. This was followed up by further work of Song Mei and his co-authors, which showed that even if the input dimension diverges to infinity, as long as the training time is constant, and they also extended it to unbounded activation sigma, you can also achieve an approximation between the mean field neural network and the finite width neural network that decays with the width of the network. And this was applied in some work by Emmanuel Abe and his co-authors to solving a really interesting class of multi-index problems called merge staircase problems that a lot of people cared about. And they used this mean of field approximation to do that. And all these problems were able to be solved in a training time that was constant. And so for beyond training times, this work by myself and some of my co-authors at Stanford established that for training times that are on the order of log d for some simple classes of quadratic problems, it is also possible to show this tight coupling between the mean field model and a polynomial width model. Okay, and there are many works showing the connections between the mean field model and the polynomial width models, in particular in the world of mean field Langevin dynamics, where you add noise. This coupling is a lot easier to show, but I'm not going to mention all these works. So building upon these works, though, it's been observed through a lot of works on feature learning in neural networks or via gradient descent that more challenging problems often require polynomial and d time to train for. So a couple examples of this are learning single index models with a high information or generative exponent. So it's OK if you don't know what that is, but a single index model is when we're trying to learn some ground truth function. F star of x is some activation applied to the projection of x in a single direction W star. And if this activation function phi is very challenging, for example, it looks something like this, it has some very flat saddles, non-monotonicity, etc., then it's possible that learning this function via gradient descent takes polynomial time in D, which is the dimension of x. And another problem which takes polynomial and the dimension time to learn is parities. Okay, so let's further refine our main question. Does the behavior of a polynomially wide neural network well approximate infinite width neural networks for polynomially long training times? So before I get to my result, I just want to say one thing about why this is challenging. So we can think of our mean field neural network and our finite width neural network, which I'm denoting by rho t mean field and rho hat t superscript m, where m is the width of the finite width neural network, as evolving in some landscape because they're evolving via gradient dynamics. In fact, this landscape is a landscape that's like plotted with the Wasserstein 1 geometry because it is actually the case that gradient descent in a mean field neural network is gradient flow in the Wasserstein space. And we know that at time 0, when this neural network is initialized, the function output by the width m neural network and the function output by the mean field neural network are actually very small. The distance between them is very small in L2 distance. It scales like 1 over the square root of the number of neurons. And this is via a very simple Monte Carlo argument. But because this landscape is non-convex, even a small deviation can blow up exponentially in time between these two different neural networks. Because as they evolve via gradient descent in this network, if they're slightly further away, then their gradients can also be slightly further away, and so they drift apart. And so if this landscape is L-smooth, in a certain sense that depends on this Wasserstein geometry, then one can achieve this typical Gronwall bound that tells us that at time t, the distance between the functions expressed by these two networks is going to be bounded by exponential in L times t times the initial distance between these two neural networks. And so this gives us a bound which is strong whenever t is small, but if t is going to grow polynomially in the input dimension d, it's going to suggest that that the width m, in order to achieve a close approximation, is going to have to grow polynomially is going to have to grow exponentially in the input dimension. Okay, so our main result is able to overcome this. So we study a setting of two-layer neural networks where the first layer weights are all constrained to the sphere, and the second layer weights are fixed at 1. And we're in a teacher-student setting where we're trying to learn a ground truth function f star, which has to be expressed by a teacher network that only has finitely many neurons in it. And we're training via projected gradient flow, which means that we do gradient flow, but we, at every step, we project the neurons to stay back on the sphere. And our main results show that if a certain set of assumptions hold, which I'm going to show below, then with high probability over the initialization of the neural network, the distance between this mean field neural network and this width m neural network is going to be bounded polynomially in d in the time, and this extra parameter j max, which is some sort of local stability parameter, divided by m, the width. Okay, and these are the assumptions. I don't have time to get into them, so I'll just leave it at this. And if you have questions, feel free to ask about the assumptions or anything else.
Thanks for the great talk. I think we have time for one question before the break.
Hello, nice talk. So maybe this is part of your assumptions, but how do you handle the case when there are saddle points in the training dynamics? So I guess like, are you only comparing against gradient flow? Because I guess like the mean field dynamics can get stuck in the saddle point, but like the actual dynamics wouldn't. So what happens in that case?
Yeah. So in the so our analysis can work in the case where there are saddle points. All the settings that we were able to apply this to, so in fact, we actually only applied it to the setting of learning a single index function, though this result is more general, the examples we have are that. And even in that case, for a mean field, for the mean field dynamics, even though there are saddles in the landscape, the initialization is still a little bit away from the saddle. Because like every neuron, if you think about, for example, a single index model, even though there are saddles, if you're initialized with a 0 projection onto the ground truth neuron, most of the neurons are going to have like a 1 over square root of d distance. So you're going to have a little bit of distance from the saddle. So if the mean field dynamics get stuck in a saddle, then it might be the case that the conditions of the theorem don't hold if the finite width dynamics don't get stuck in a saddle, or it might be the case that it also gets stuck in a saddle. I don't know. But yeah, theoretically, you can handle saddles. Just, yeah.
Thank you.
Okay, yeah, let's thank Yami.
Hi, very nice. Do you have like examples of concrete data sets, like concrete problems where all of these conditions are satisfied with reasonable sizes for the various parameters?
Okay, yeah, I have another slide that I just stopped because we're out of time. In this problem, for example, the problem of learning a well-specified single index model, we can satisfy all these assumptions. We do it in the case of a single index model with an information exponent that's more than 4, because that leads to polynomial and D training times. So that's the setting that it was interesting for. Theoretically, it could also work for single index models with a lower information exponent, but existing results already cover that. So yeah, this will satisfy all the assumptions. We're working on broadening the set of problems that the assumptions hold for.
Thank Margaret and all of the speakers for a great session. And there's an announcement from the local chair.
Yeah, short announcement before the pause. So 2 things. If you don't have a ticket for a restaurant tonight and you want to go to some of them, just go to the registration desk now. They still have a few places at different restaurants. Second thing, if you have a visit of Lyon this afternoon, which is planned, please be on time. You should have on your ticket the place where you should be exactly at 2:40. So please respect that, because otherwise they won't wait for you. So enjoy your day.